Hello, everyone. Good morning, good afternoon, and good evening, young professionals. I welcome you today for the IEEE Young Professionals webinar series for the month of June. Today, our speaker is Dr. Quenton Bonds, and he'll be speaking about NASA's Wideband Instrument for Snow Measurements Radiometer, shortly called WISM Radiometer. Quenton currently works as the research electronics engineer at NASA Goddard Space Center and also is the founder of the Accelerated Destiny. Please feel free to read more about Quenton on the live page description below. I'm Preeti Kovvali, your host today. I'm part of the Global Young Professionals team and currently working at an India-based technology services firm called Tech Mahindra. IEEE Young Professionals hosts monthly webinars on selected topics of your interest in the leadership and technical areas. Do follow our website and social media pages for the upcoming events list. For all the audience out there, should you have any questions now or during the webinar or after the webinar, please feel free to post your questions in the box below on the IEEE.tv page. All your questions will be answered during the Q&A session post the webinar. Follow our website yp.ieee.org for updates on IEEE Young Professionals. You find amazing resources for members and volunteers along with stories of our IEEE Young Professional members and volunteers on impact, which is of course by and of our IEEE Young Professionals. IEEE Young Professionals partners with key global IEEE and non-IEEE events to host young professionals meetups. These are one of the most happening events across the world. Here on your screen is a list of some of the coolest events that are hosted and to be hosted across different IEEE regions. You will find more information about this on our IEEE Young Professionals website and our social media. We are spread across the social media. Follow us on Twitter right away and tweet your webinar experience and like us on Facebook. Do not miss out any latest updates by IEEE Young Professionals. Write to us on the email ID, which is as shown here on the screen. We also have our own YouTube channel where you will find the archives of all the webinars and also other exciting videos of big personalities in technology and engineering. We have our internal community called IEEE Collaborate. Please join right now. This is open for all IEEE and non-IEEE members. This is an amazing way of networking and a collaboration site for technology professionals across the world. We will now begin with our webinar today on WISM Radiometer by Dr. Quenton Bonds. He'll be speaking about the project as an overview, GSFC accomplishments and the science experiments involved, and the current status of the project and the path forward. So thank you so much, Quenton, for accepting our request, and it is now over to you.
Thank you so much for the introduction. I also want to let everybody know that I'm honored to have the opportunity to give this webinar for such a distinguished group, the IEEE Young Professionals. And I've been excited about this webinar for a while. This is one of the most interesting, exciting projects that I've worked on from undergrad to even being a professional. So I'm going to take you on a little journey of our WISM radiometer. I'm going to talk about just like Preeti said, we're going to talk about the current status, the path forward, and some of the things that we've accomplished. Expect the talk to be about 35 to 40 minutes. It's not going to be a full hour, But I'm looking forward to your questions at the end. No question is a dumb question. No question is a stupid question. The talk is going to be technical. It's going to be, some of it's going to be non-technical. But let's get into it. So this project is actually a collaboration with multiple organizations. I work for the NASA Goddard Space Flight Center. NASA Glenn also is a collaborator. Harris is the actual PI, the Harris Corporation. Nuvotronics is developing the antenna. The University of Washington is developing the algorithms for the snow. I'll talk about those later, the snow retrieval algorithms. And Boise State is doing some radar work, and they're also developing the radar algorithms. We're not listed here. One of our collaborators also at the University of Colorado. The principal investigator, Tim Durham, he's at the Harris Corporation. The co-investigator, Paul Reset, he's kind of like the guy that's over the project, and I'm the lead radiometer systems engineer. But we do so much more. Preeti's already given you an overview of the presentation, so I'm not going to spend a lot of time on this. But basically, we're going to talk about our accomplishments, show you what we did in the science experiments after giving you an overview of the project, and talk about our current status and path forward. Okay, I'm not going to spend a lot of time on this chart, but here are a few takeaways. This is kind of a chart so you can look at this after the presentation and get an idea of why we want to measure snow. But this is a ROSES IIP. NASA has an instrument incubator program, so people from industry actually can write grants and proposals to build NASA equipment. And in this case, Harris wrote a proposal. They collaborated with us, with NASA. That's the best way to win one of these ROSES proposals. And this one was to support the Snow and Cold Land Processes mission, where obviously the idea is to measure snow. And I'll talk to you a little bit later about why snow is important. From an RF and microwave standpoint, for my RF engineers out there, we're operating a SAR, we're operating a radiometer, and we're operating a Lidar over multiple frequency bands. And the key enabling technology is the antenna. It's the current sheet array antenna. It's down in the bottom right-hand corner of the screen. That antenna is probably about 4 inches by 4 inches by probably like an inch and a half, whereas a feed that can cover all these frequency ranges will probably be on the order of 1.5 feet, or okay, you guys are in meters, so probably about 0.5 meter to 1/3 of a meter tall. Because we're operating over the X band for a SAR, the KU band for a SAR, the radiometer we're operating at the KU, KA, and X band. We're operating at horizontal and vertical polarization. And what enables us to perform this technology is that antenna is excited at all of those frequency bands. So all of those frequency bands share the same antenna. The blue structure to the right is kind of a reflector. And if you look at the spacecraft at the top, the antenna excites the reflector, and the reflector actually takes the measurement of the snow on the ground for a radiometer, a radar, and a Lidar. The radiometer and the radar are physically connected together. The Lidar is separate, but we use kind of all of this data to measure snow water equivalent. So that's kind of an overview of the project. Once again, you can kind of look at this afterwards. But the key takeaway is the multiple frequencies sharing the same antenna, radar, radiometer, Lidar, and we want to measure snow water equivalent. So why do we want to measure snow water equivalent? This is where the cool parts start. Okay, so in the U.S. and abroad, 50 to 80% of the water supply in certain places, particularly out west in the U.S., are from snow runoff. What that means is, and if I can give you an example, I think everybody's kind of heard of Yosemite National Park, Yosemite Sam, it's kind of a cartoon. I think a lot of people heard of it. But Yosemite National Park has a bunch of waterfalls. These waterfalls are a derivative of snow runoff. So snow falls, it melts, it produces these waterfalls, and that kind of go year-round. But what a lot of people don't realize is that snow runoff affects a lot of things. Particularly, it affects, theoretically, the weather. So snow falls, it evaporates, it melts. When it evaporates, it affects the weather. Theoretically, that affects climate change. Theoretically, that kind of affects the global climate cycle. The broader impact of this is that if we can kind of measure snow, a lot of countries that are third world, a lot of countries that are underdeveloped, we can kind of manage water resources around the earth for people that don't have water. It's a lot of different challenges here because We want to measure snow on a small scale because if you look at my pictures down in the bottom left-hand corner, the snowpack varies wildly. So you want to be able to accurately measure this. So for WISM, we actually not only have a radar, radiometer, Lidar, but we have ground truth measurements validating our snow measurements. So what ground truth is, someone is there taking measurements on the ground with the radar, and people actually digging snow pits to determine, hey, if we took these measurements of snow void equivalent, snow depth, snow density, we call these snow parameters, are our measurements accurate? Are these measurements performed correctly? And the ground truth to help us validate our measurement. And what we usually do at NASA is, before putting these instruments in space, because this is a demonstration of concept, it's not in space yet, we fly them on an aircraft. So you'll see from some of my subsequent slides that this instrument is deployed on an aircraft, pointing 45 degrees outside the door of the aircraft, looking at the ground, looking at snow on the ground over the Grand Mesa in Colorado. You can see kind of my concept image to the right. It's a space cube. Not to say we're going to deploy this on a space cube, but space cubes are becoming extremely popular with NASA. Instead of sending these huge billion-dollar missions into space that can only measure a few things, why not send smaller space cube payloads? Now, I would say that payload is probably like a half a meter by a fourth of a meter cubed. And once again, we want to measure snow year-round in orbit, probably low Earth orbit. We haven't kind of decided. And so we do this project, WISM, a demonstration of concept on an aircraft, to vet the technology before we take it up into space and put so much time, money, and effort into developing a spacecraft instrument. And so I mentioned other organizations, but our primary role at Goddard was to develop the radiometer. In context of snow, the radiometer is a passive instrument, meaning that it only detects. All right. The radar is active, meaning that it sends a signal and receives a signal. The Lidar is active, but the Lidar is not integrated physically with the radar and the radiometer. Lidar is deployed under the aircraft, and I'll talk about that, I think, on the next slide. But the radiometer and the radar, if you look at the block diagram, they're physically connected together. They share the antenna. It's a reflector. That reflector looks out the door of the aircraft. The antenna excites the reflector. The reflector looks out the door of the aircraft at 45 degrees, and we have a black body calibrator. That's what this piece of equipment to the right is. The golden part that's directly in the center of the picture, that's the actual antenna I was telling you about, 4 inches by 4 inches. That dish is about a third of a meter in diameter. So that antenna excites the dish. The dish is looking outside on the ground. Probably for the radiometer footprint is probably about 93 meters to 150 meters, depending on the altitude of the aircraft. And the way this thing works is that we operate interleaved with the radar. What that means is our sampling rate is 100 kilohertz. That means that it's the duty cycle 80 to 20. So at 100 kilohertz, the radiometer is taking data. And when the radar transmits, we actually blank the radiometer. So what that means is that the radiometer, the calibration load, internal calibration loads of the radiometer, we pretty much put it in protection mode so that the radar can transmit. But the radar is only transmitting about 20% of the time, but it's sending a lot of signals very fast. And I kind of talked about the different frequencies on the introduction chart, and I'll get more into the calibration. I have a chart specifically on calibration. So this is kind of the block diagram, and that's the actual radiometer. That's the actual antenna and reflector that we use. So what have we accomplished on this project? This project has been ongoing, I think, from about 4 to 5 years, and we started out with just a PowerPoint drawing, that's before I even knew how to use Visio. And you can see this is kind of my Visio block diagrams. I've come a long way since PowerPoint. And what we've actually accomplished is that we started out, as you know, for those of you who are RF and microwave engineers, if you look in the bottom right-hand corner, we start out with our laboratory benchtop testing. Not shown here is that we test the individual components. There's 2 radiometer bands, the KU and the KA radiometer band. Later, we added an X band, so we did a KU, KA radiometer band. We did a science flight, then we added an X-band radiometer. But we characterized the individual components, then we characterized the subsystem in the radiometers. Then we put the radiometers into the box, characterized the instrument inside of the box. Next, we go up, and if you look from the bottom right-hand corner to the image immediately to the above it, we go to the rooftop of one of our buildings at NASA, and we take cosmic background radiation measurements because we know the brightness temperature of those cosmic backgrounds. And what I did or didn't do such a great job of mentioning is that a radiometer detects brightness temperature. And how that is related to snow, the brightness temperature pretty much gives us the density of the snow when we measure it at a few different frequencies. So KU and Ka band have different wavelengths. Based on those different wavelengths, the scientists put that data into an algorithm which gives us the density of the snow. The Lidar and the radar, since they're active, they send a signal and receive a signal at a few different frequencies. They can kind of give us the density of the snow and give us the depth of the snow. And the radiometer kind of also helps with the density. You put all this together, you can kind of determine for our footprint, which is what I mentioned about 93 meters, you can kind of determine the snow water equivalent in that particular snowpack. But this process that I show you here is our integration and test. So after we do the benchtop test, individual components, the complete box, we take the cosmic background measurements, we go to Harris, that's the PI as mentioned before, we integrate the radiometer with the radar and the antenna there, then we take the instrument out to the field, we perform the measurements over the Grand Mesa in Colorado. So the image to the left in the top, the silver instrument, that's the actual radar. You've seen the reflector in the antenna, and the science experiment, bottom left-hand corner, that's us actually integrating the instrument on the aircraft, and we fly over the Grand Mesa at altitudes of about 3,000, 1,500 feet, 3,000 feet, and 500 feet. I'm sorry, I said that wrong. 1,500 feet, 3,000 feet, and 5,000 feet, not 1,500. So here's kind of an overview of our radiometer. You can see if I start in the left-hand corner, we connect the radiometer to control the instrument to a what we call a KVM. It's just basically a video monitor. And we actually have a GUI on the radiometer itself that we use to control the instrument. And we can change our different calibration modes. I'll get into calibration a little bit later. The aircraft provides us 28 volts DC. We have a bunch of power systems inside the instrument to convert down to the voltages of our individual components. We have an external thermal system that we use to control the temperature of the antenna. And we have our RF outputs that actually feed into the radar. This instrument is also connected to a GPS during flight, so that we'll know our exact position when we're measuring the snow. And around the end of the chart, you'll actually see some actual measurements where you'll be able to see kind of the variation in the snow. So here's a chart about calibration. Most of our RF and microwave guys probably get really excited about this, but basically we have two physical loads, one ambient and one actually cooled with the thermoelectric cooler. We also have two noise sources. So we use these ambient loads, these physical loads, to calibrate our noise sources, and we use a noise source and an ambient load to calibrate the instrument where the antenna comes in. So the concept here is basically, if you think of a straight line, for radiometers, we detect a brightness temperature. That brightness temperature is a function of the output voltage from our instrument. So if I have a cold target that's physically cooled, that target will provide a voltage. A hot target, which is my ambient target, is hot because it's warmer than snow. That particular calibration reference provides a voltage, and we're measuring snow, which is in between those two calibration loads. So that, in general, that's how we translate brightness temperature from voltage. So if you just think about it conceptually, we know the brightness temperature of our physical standards, and when we take these measurements, we use kind of that equation of the straight line to calibrate and figure out what is the brightness temperature of the snow that we are measuring. And so I mentioned before that we do benchtop testing. We measure the individual components, and the picture to the right is kind of me doing like our final benchtop testing. We actually look at liquid nitrogen and an ambient load. We look at the data digitization. Basically, we run our data into a A to D, and basically, does the resolution look right? So, you know, if we have a 16-bit A to D, are we seeing, you know, 2 to the 16 counts or count steps? By calibration sequencing, are we sequencing through our calibration loads properly? Are noise sources turning on properly? Is the instrument thermally stable? And this is kind of a video, I hope it plays, of me. It's actual liquid nitrogen in that bucket. 77 Kelvin is the brightness temperature of that liquid nitrogen. And the other target is an ambient target at room temperature, about 300 Kelvin. And we look at both frequency bands, KU and the KA band, and that's how we calibrate the instrument to validate the performance before taking it to do the rooftop and other lab testing. So after we characterize the instrument by itself individually, we come back and we connect the antenna. Remember, the antenna is the key enabling technology. So we connect the antenna to the instrument and we perform even more characterization. That on the floor, for those of you that aren't RF and microwave engineers, that's actually absorber on the floor. So that is kind of a black body for us. We kind of know what that looks like. And not shown here is that we can actually take the radiometer into a lab at NASA Goddard. We have a cold room where we can fill basically coolers up with different levels of snow, take measurements, go back and process that data to determine is our instrument functioning properly in somewhat of a pseudo real live environment of actually measuring snow. And that's me kind of integrating the antenna with the radiometer and the radar. And I had to be very careful because I think those antennas run about $500,000 a piece. It's very delicate. And so you see me with my gloves integrating the antenna with the actual radiometer. And before I go any farther, I would be remiss not to kind of let you guys know I didn't do all this by myself. Paul Reset helped a lot with the calibration. Troy Ames and Tom Winkert, and I'm probably missing other people. Beth Timmons, they helped out with the data system. They pretty much developed the data system. The thermal system. We had a team kind of helping out with the thermal system. We also had a team helping out with the actual mechanical integration, people within our branch. So this was really a team effort. And you know, I just kind of wanted to highlight that because I missed that in the overview. So after we do our benchtop testing, we integrate the radiometer with the antenna, and we actually take cosmic background radiation measurements on the roof. And you can see me down in the bottom right-hand corner. That's the radome. That is going to be on the door of the aircraft. Remember, we fly the aircraft above the ground mesa at 1,500 feet, 3,000 feet, 5,000 feet. And I'm sorry, meters, 1,500 meters, 3,000 meters, and 5,000 meters above the Grand Mesa, and we're looking out of the door of the aircraft, and that particular radome there will be over the door, so we have to characterize that radome. So we actually characterize that radome, and those measurements that you see right there, I use those measurements to correct for the loss that's in that radome. A radiometer, once again, is passive, and it detects signals on the order of 1 to the negative 16 and lower for snow. Room temperature is about 1 to the negative 16 watts. So snow radiates probably lower than that. Room temperature is 300 Kelvin. Snow, I think, is around 220 Kelvin. So you can just see the small signals. The gain of this radiometer is about 60 dB. So we're detecting very, very small signals. So any loss in front of that radiometer, we need to correct for it. And when we take our cosmic background radiation measurements, we look straight up, we look zenith, we pull the data from what they call the radio sun. The radio sun, they have those at various weather stations. We have one at Goddard, I think we're very close to Goddard, and it tells us what's the brightness temperature for cosmic background radiation at zenith looking straight up, and what is it at 45 degrees. So since our antenna is pointing 45 degrees, if you just put a metal reflector there, we can measure at an angle of 45 degrees. And if you just tilt it up at an angle of 22 degrees, you can see we can measure zenith. And we measure a black body, and so that black body, we actually have one on the inside of the room. That's a warm black body, and we leave one outside to kind of give us two different temperatures. All of this is before we put the instrument on the aircraft to demonstrate the concept to take this to flight. Here's some of the data. That's an example to your left of some actual radiometer data from these measurements. What I wanted to show here that not only do we do RF and microwave, I played a big role in this design of the box. A lot of people ask me, why did I put a clear window on top of the box? I don't know if you can see it. I'm going to try to find it. Here's a good picture. You can see I put a clear window on top of the box, and I did that because I used to sell car audio equipment. I used to sell amplifiers when I was a little boy in high school. That's what got me in electrical engineering, and all the amplifiers had a clear window on them. So I designed this box to have the same thing because I wanted to look in there also to see if it's a problem. But back to the measurements. These are, like I said, these are actual radiometer measurements with our radiometer, and I wanted to show that not only do we do the box design, not only if necessary do we do the RF. I'm an RF and microwave engineer, but I'm also processing data. So as you can see, there are spikes in this data to the left. So I had to develop a spike removal algorithm to take these spikes off without compromising the integrity of the data. It's kind of on different scales, so it's a little bit hard to tell, but this is actual radiometer data that has been filtered. That's what we call it. So we do a lot of different things after we build it, test it, and characterize it. Actually, it's a lot of the data processing is a pretty significant effort. I mentioned on the calibration slide, I didn't talk a lot about it. I'll go back to the calibration slide. Sorry about the delay. So going back to the calibration slide, we're actually switching through, even though we have 4 references, we have 6 different calibration modes. So I can look at the warm load as a calibration point, the hot load, the antenna, the noise source 1, noise source 2. I can look at the cold load plus noise source 1, cold load plus noise source 2. I can look at all these different calibration loads, and from this, once again, we're sampling at 100 kilohertz, right? So, I'm sorry, yeah, 100 kilohertz. We're sampling at 100 kilohertz. We're looking at 6 different calibration loads. So just imagine taking data at 100,000 samples per second, switching through 6 different calibration loads, and these different calibration loads are helping you to determine what's the brightness temperature of what your instrument is looking at. So so I just want to just show that the data processing is a pretty significant effort. And you get your data back and you have spikes in it. So what do? You have to design some type of filtering algorithm to get these spikes out. So after we validate the performance of the instrument, you can see me in the bottom right-hand corner boxing the instrument up to take it to sunny Melbourne, Florida, to integrate it with the radar at Harris. And once again, the radar is kind of the silver box that's standing vertical, and we integrate it with the radar, and we do interference testing because the radar can actually damage the radiometer. I think the radar is transmitting about 5 watts, but the radiometer is expecting to see signals on the order of 1 to the negative 16 watts and below. Again, 1 to the negative 16 watts is room temperature, brightness temperature. Well, it's not a brightness temperature, it's the wattage that's equivalent to a brightness temperature of 300 Kelvin. And snow is colder than that, so we expect to see something smaller. And, one of the main tests we do is the interference testing. Just to kind of explain these charts now here. When the radar is off, you kind of see this hump to the left. That's one state of the instrument. That's one calibration state. That's the antenna state. But when the radar is on, you can see the little kind of spikes or indentations in that particular sample. And I would probably bet my luck that 20% of that, I would bet my luck that between these 2 signals, 20% of this is radar and 80% of this is radiometer because we're operating at an 80-20 duty cycle. And so it just shows that this shows us that our radiometer is blanking when our radar transmits. So remember, when the radar transmits, we throw the radiometer in protection mode. If you know, we were expecting to see, you know, 5 watts. You see huge peaks, spikes. If the radiometer was not blanking the radar properly, you'll see these huge spikes. But you can see here that every time the radar is on, the radiometer, you don't see any significant huge spikes. And the top chart is kind of the state that the radiometer is in, and actually the bottom chart is actually the actual radiometer data. So after we perform our testing at Harris, we do our science experiment. And one thing that I want to highlight here, even though, you know, at Goddard we kind of do a lot of different things, even though I'm the RF and microwave engineer, I had to kind of identify where will we put these instruments. So I did a little trade study on a few different aircraft, the P3, the Twin Otter, and the Twin Otter is the aircraft that we end up going with. And I actually had to look at the data sheets or the diagrams for the aircraft, measure out the bomb bay, can our lidar fit in the bomb bay, can our radiometer and radar, can it point out the door? So I pretty much did this as well. We had people to help, but this kind of was something I was responsible for. So not only did we do the RF, not only did we do some mechanical, there was a lot of different things that went into this project. And as you can see, that's the lidar in the bottom right-hand corner. We put it in the bomb bay. The fuselage is kind of like a cut of the fuselage. You can see the radiometer is pointing out the door, and the radar is behind the radiometer. And so here's some pictures from our actual science experiment. We did this over the Grand Mesa in Colorado. It's cold, so you can see me down in the bottom left-hand corner, bundled up with my running gear on. To the right is the radiometer. The radar is behind the antenna. That box around the antenna is an ambient black body, because we don't want the antenna picking up on the we don't want the back lobes of the antenna picking up on the temperature inside the aircraft. And that structure, if you go up one, the structure to the right-hand corner is our reflector that we do the cosmic background radiation calibration. In the right-hand corner, it's at 45 degrees. Remember, the instrument is pointing 45 degrees. Go to the left, one block in the upper left-hand corner, we can see that we can point zenith just by tilting our calibrator up. And you know, at cosmic background, I think at KU band is around 9 Kelvin or something. I think at KA band is 16 Kelvin. Depending on the day, I might have those two switched around. But we also take measurements with a cold and a hot black body. So in the bottom left-hand corner, that box has absorbent inside of it. And we're looking out of the door with the radome in the front. Remember, I characterized the radome. And once again, we're taking measurements at 1,500 feet, 3,000 feet, and 5,000 feet. I think I mentioned meters before. But you can see we actually measure the temperatures of these of that box, and I have to design a program to import those temperatures to a pre-flight calibration. So I have to design I have to write a program. I use MATLAB to import those box temperatures to see the pre-flight calibration. So we calibrate before the flight and we calibrate after the flight. And you'll see later why that's significant in our data processing. And so here's some pictures. If I start at the top, after we flew the instrument, we actually went to the site. So that's the Grand Mesa. And those guys in the background, we actually dug snow pits and looked at the snow. This is me in the aircraft flying over the Grand Mesa, and the instrument is looking out of that same angle that I'm pointing the camera. So it's looking at 45 degrees. It's looking at the ground, and that's our snow-on measurement. And it's beautiful up there. So we're flying, I think, about 3,000 feet in the air. I don't know what that guy's talking about, but you know, that's kind of just some measurements at the site there. I mentioned about the data processing. It's a pretty significant effort. I'm not going to spend a lot of time on this, but basically we convert the data from binary to decimal. We remove any spikes. We apply the calibration. We do averaging. We do even more correction. We use the pre-flight data to calibrate the flight data, because our internal calibration loads are accurate, but we have a lot of loss at the front end, about 12 dB on the KA band. We just found this out a few months ago, and we got 8 dB on the KU band. That's 4 dB more than we thought we had a few months ago. We have to geolocate the data, so this data processing is a pretty significant effort. And so we performed another science experiment, this time with no snow. So we performed one science experiment with snow, another science experiment with no snow. Same site, that's the aircraft. We do those pre-flight calibrations. Those reflectors to the right, those are the radar reflectors. So those reflectors were also out there in the snow when the radar was taking measurements. The bottom left-hand corner, that's a picture kind of us flying over the airport. The radar calibrates by flying over the airport. And you can see me down in the right-hand corner kind of controlling the instrument as we fly over. And the guy in the upper right-hand corner, he's operating the radar. To the left, we generated this data immediately after the flight to show that our radiometer was working properly. Our data processing algorithms were not that advanced during the first flight, the first snow flight, which was February 2015. Our algorithms were not that advanced to be able to provide this data. But at this flight, which was October 2015, we were able to provide some data about, I think, 24 hours after the flight. We are proposed to fly again in August, and we could probably even provide even better data. But you can see that if you look at the lakes, you can see how the radiometer detects the brightness temperature of the lakes as we fly over the lakes. So those spikes that's going in the downward negative direction, that's just the radiometer measuring the lakes. The lakes are colder than the ground, as you probably know. The Grand Mesa, I think, is at 10,000 feet. So that kind of validates the performance of our instrument. I'm not going to spend a lot of time on this chart. It's just showing that, hey, some measurements we get data, some measurements we don't get data. Sometimes the problem is as simple as when I pull the science, we have science and telemetry. The telemetry is the temperature sensor data. The science is the actual radiometer measurements. When I pull this data off of the data system, you know, I think one time I thought I had all the telemetry data, but when I got back to Goddard, I realized the telemetry data didn't copy for whatever reason, so I can't use that measurement. So anyway, we show, you know, how many hours of data. We have another chart that we show, you know, how many megabytes or gigabytes, really gigabytes of data that we detect, just so that, you know, if we come back and need to figure out, oh, what did we do? Can we validate the performance of our instruments? We'll know that, you know, we took this much data on this day, this much data on Saturday. Let's try to compare the data from Saturday and Sunday. Do we have the right data set? Yes. You know, it's you know, this many gigabytes. So what is our current status? We took the data from the first science experiment. We enhanced our algorithms. If you look at the chart to the right, you can see that as the radiometer flies over the lakes, the brightness temperature decreases, which is exactly what the science expects it to do. If you fly over trees, the canopy, the brightness temperature increases. Trees radiate more brightness temperature. It's consistent for the Ka, which is the top, and the Ku radiometer, which is at the bottom. So to the left, that's kind of the raw data. To the right, that data has been calibrated. That data has been calibrated and geolocated over the spots that we fly over our snow. The snow is not shown here, but this is actual data that we took over the snow. This is just a different type of graph. I forget what they call this. It's just a different view, but you can see here it's still consistent. If you look at the lakes where the arrows are pointing, again, the brightness temperature is a little bit cooler. At canopy, you can see the brightness temperature is warmer. Canopy, for those of you who don't know, those are just the trees. Once again, I just kind of show the raw data between two different flights. And now we're trying to correct our calibration. So we use the pre-flight data to correct the flight data. So I designed a calibration algorithm. I don't think I show it, but I designed a calibration algorithm to characterize all the losses in the front end of the radiometer. And theoretically, my calibration algorithm, that's the pink curve, L1D1. It should line right up with our pre-flight measurements. So the pre-flight measurements, what we took with the warm box, the cosmic background radiation, that's what you see in the blue dash line. In the cosmic backgrounds at 45 degrees and 90 degrees and zenith are the black dotted lines and the blue solid line respectively. And so this radiometer data should line right up with this, but it doesn't for the pre-flight. We have to apply an optimization to the model that I developed to correct the losses in the front end to make those measurements line up with each other. And that's what you see here after I apply my optimization. The blue and the kind of orangish curves, they kind of line right up with the pre-flight, which is once again the dotted line. The red dotted line is the warm blocks. The black dotted line is Ka, looking at 45 degrees cosmic background and 0 degrees cosmic background. And we're still working on this. And so we're going to fly again, like I mentioned, around September of this year. And these are just some things that we need to do to make a few updates before flying again. After every flight, you kind of realize you have some problems. And we had some problems with the flight. And I think I have been talking long enough. So now I want to give you guys and ladies a chance to ask questions. This is kind of my favorite part. Once again, no questions a stupid question. Love to share technical, non-technical. Preeti, I'll let you have the floor.
Thank you, Quenton, for presenting that amazing session to all our viewers today. I do have a few questions lined up for you. Let me refresh the screen just a minute. Okay. So the first one is from Tushar, United States. Can you explain how graduate students get involved in such missions?
Yeah, so that's a great question, Tushar. It's a few different ways. So one, I'm going to give you the conventional way, and I'm going to give you the non-conventional way. It'll be great, like if your advisor was working on projects or collaborating with NASA. That's not so easy to do, but I mentioned about these ROSES proposals. And Preeti, she can provide my email after the session. But I think just about anybody from industry can collaborate with NASA on ROSES proposals, or they can collaborate on SBIRs, science, business. I forget SBIR, what it stands for. You can look it up. So if your advisor doesn't have a project with NASA, you can kind of say, hey, you know, NASA's doing some cool stuff that's related to what we're doing. Let's try to collaborate with them. You know, that's kind of a little bit of an unconventional way of doing things, because usually the conventional way, your advisor already kind of has already kind of has a collaboration with NASA. Another way to do it is to apply for the internships. And I know it's hard because a lot of people are international, but looking at JPL, JPL is actually kind of sort of our competitor because we both do some of the same things, radars and radiometers. But see if JPL is offering any internships or things of that nature. And I think it's also good to know people. So if you find something that you want to do, you know, maybe email me, and maybe I'll send some emails out. It's hard right now because NASA's not hiring, but going to the conferences and meeting people is a great way to do it. If you find somebody working on things that you find interesting, that's a great way to kind of collaborate on such projects as well.
Okay. Next question is from John, Brazil. What type of antenna is being used in the system? Is it optimized for instrument, or is it just assembled?
Yeah, so John, that's a good question. The antenna is actually what we call a current sheet array. It's Nuvotronics technology. It's kind of their proprietary technology. So I've designed antennas before, and I don't quite fully understand this technology, but they use what they call micro coaxes, which look like just like very small waveguides, but they actually have like some type of propagation, like a pin in the middle. And the antenna is not really optimized for the instrument, but it's optimized for our frequencies. So at the radiometer KU, radiometer KA, radiometer X, theoretically, we're trying to optimize this antenna to function at those frequencies. Once again, we also have a radar. So the radar KU, the radar X at horizontal and vertical polarization. The radiometer is just horizontal polarization. The antenna is kind of optimized to operate at those frequencies. And we even had some challenges with the antenna, because I think I mentioned to you guys that we had about 4 dB more of loss than we expected. For those of you that not familiar with dB, that's probably about, I think, 58 to 65% more loss than we expected. We already had a bunch of loss. And part of that loss was because at certain frequency bands, the antenna had a lot more loss than expected. And I have a chart here. I'm not sure if you can see it, but the antenna is, once again, it's about 4 inches by 4 inches by like an inch to inch and a half. And I don't show the bottom of the antenna, but about 4 or 5 cables connect to that antenna. One of those cables is the radar and the radiometer integrated together at the X band and integrated together at the KU and the KA band. So they all share the same antenna. So it's not really a patch. There are radiating elements. I think it's like a 3x3 radiating element, but they're excited by this current sheet array, which has multiple feeds, allowing you to feed multiple frequencies. So I hope that answers your question the best way I could. Next question.
Next question is from Andy Zhu, who's from United States. How sensitive is the instrument to calibration techniques? What type of cal techniques are used?
Yeah, so you guys and ladies ask great questions. The instrument is extremely sensitive to the calibration. If I can explain this calibration a little bit more, I'll go to my calibration chart. It's a little bit of a delay. But so it's a lot of different calibration techniques. This one is the fact that we use those. It says load, ambient, TB is ambient. Ambient is whatever the room temperature is. Once again, around 298 or 300 Kelvin. And we have another load which is 30 Kelvin colder. I have TB equals 30, but it's actually not 30 Kelvin. It's 30 Kelvin colder than the ambient target. And since it's a separation from those two calibration loads, ambient provides a brightness temperature and a voltage. Ambient minus 30 degrees Kelvin provides a brightness temperature and a voltage. You can form a straight line between those two and calibrate the noise sources, because the noise source is going to provide a brightness temperature and a voltage. And based on your calibration line, more than likely your snow measurement will be between, you'll get a voltage out between the voltage and the respective brightness temperatures of your calibration loads. And you can just use the equation of a straight line to get the actual brightness temperature based on that voltage. That's the easy part. But the hard part is when you have a bunch of loss in the front end, which we do. So then you have to develop a model of your complete front end, a mathematical model of every component in your front end, which I really don't show in this presentation. But this is kind of a general overview. So your mathematical model has to correct for the input matching the antenna. It has to correct for the loss in the triplexer. It has to correct for the loss in the cable. Has to correct for the loss in the radome. Has to correct for the fact that your antenna is only pointing in one direction, and you can't, and it's not measuring all, or it's not omnidirectional. So it's not measuring all around. It's only measuring in one direction. So you have to correct for all of those losses, and you have to take measurements on the bench for all of those different components. The problem is, as you know, if you're an RF engineer or any type of engineer, during the flight things change, right? So the temperatures change, which changes the performance of all those components. So at that point, this is what I'm trying to do now, is I've developed this model, I have parameters, I start off with initial guesses, and I perform an optimization to match the radiometer data of my pre-flight to those calibration targets. And theoretically, if I could change my model variables to match the brightness temperatures of my pre-flight, during flight, those variables should remain the same, and I can get an accurate calibration measurement. Next question.
Next question is from Sumit Gupta, who's from India. He says, due to the global warming effects, do you think radiometer provides accurate readings for snow layers which are thinner and which have a thick layer of snow?
Yeah, all those are just really, really, really great questions. So, in order to really properly characterize snow with global warming, is his name Gupta? They got to ask the question.
That's correct, Gupta.
Yeah. So Gupta, you're right. If the snow melts and let's say it freezes again, yeah, you get a thick snow layer. But that's why we use a suite of instruments. That's why we use a radar. And radars have been known to measure snow and ice. We have radars. We have the radiometer. The radiometer alone is not the instrument. I just focus on the radiometer because that's our part at Goddard. But the radar has probably even a much more extensive, highly technical, complicated system that's measuring snow as well. You also have weather stations. You have people that do modeling of the snow terrain in different parts of the world. You have the Lidar that's flying on the aircraft. So theoretically, if we could just demonstrate this concept, we'll have a spacecraft with a radiometer and a radar taking snow measurements year round. You have another Lidar in orbit taking snow measurements year round. You have your weather stations taking snow measurements. You have your people doing your modeling, and you put all this data together. That way, you can actually measure your actual snow water equivalent, even though you might have ice sheets, you might have different layers of snow. And the radiometer and the radars, they're built to measure the different layers of snow. That's why we were out there in this picture, if I can find it. We were looking at the difference in the grain size of the snow. Here. The picture that you saw is outside in the snow. We were actually looking at the differences in the grain size. So those were little microscopes that we were looking at the time. And we could see, once they did, it was people digging snow pits from, I think, Boise State. You can see the different layers of the snow. So you can see some snow had compacted, some had melted. And just a side note, for those of you that's in grad school, I actually got a chance to ride a snowmobile for the first time. You can see the snowmobiles in the background, and I did not go slow. So it's benefits to all the hard work there. So hopefully that answers your question, Gupta.
Yes. So Quentin, we have 8 minutes to go, and there are 6 more questions. Okay, that's a lot of questions now.
All right, I'm going to try to go fast through the question.
Okay, so next is Matt from United States. Hey Quentin, how does your day look like at NASA GSFC?
Oh man, great question. So today, sometimes we have meetings. I wake up, I check my email. I usually start on whatever I left off on. So right now it's programming. So pull up the code. I'm trying to process this radiometer data. We're working on a CubeSat. So I go to some meetings about this CubeSat. After that meeting, I'm on Ansoff Designer doing a board layout for the IF subsystem, because on that project I'm not a lead. I'm just developing a subsystem. Go to another meeting, come back. For this WISM project, I'm the lead, so I'm doing scheduling. So I'm in Microsoft project developing the schedule from now into the flight campaign. So it's a combination of a lot of different things. I don't get in the lab these days as much as I would like to, but right before the science experiment, we're in the lab a lot. Next question.
Now this is from Anjali from United States. What type of radar architecture is used, and is there any manual available online for your snow instruments?
Yeah, so we build all these snow instruments from scratch, so it's usually not a manual available. We had to build them from scratch because we wanted to connect the radar and the radiometer together, because the radiometer can be damaged by the radar. And the radar is a SAR. It's a synthetic aperture radar. You can look up what a SAR is online. All right, next question.
Next is by Jenny Christian, United States. Why did you choose a career in NASA? Is industry highly paid or government agencies?
Yeah, that's a great question. In a real quick response, government doesn't pay a lot, so I didn't do this for the money. As a matter of fact, before I took this job, I was thinking about negotiating really hard, and my wife was like, well, you didn't want to do this for the money. What if you don't get the job? So I didn't even negotiate, right? Why did I choose a career at NASA? No disrespect to any other company, but a particular defense company was recruiting us after a conference. They want us to make these missile tracking systems. I tell everybody the story where I grew up. It wasn't Mr. Rogers' neighborhood. You know, it wasn't terrible, but it wasn't the easiest neighborhood. So I felt like, you know, if I wanted to kill people, I could stay at home. You know, growing up, I think even in elementary school, they tried to initiate me in the gang a few times, the Gangster Disciples. So I just didn't want to do anything that killed people. So I remember being at my desk praying and asking God, you know, for an opportunity to work for either NASA or Qualcomm. I got it. I wanted to do RF and microwave because I realized one day it's not going to be any wires anywhere, and I wanted to be on the cutting edge of that. And I wanted some experience with one of the top companies so that when it was time to get rid of all these telegraph poles and whatever they call them, all those power lines and all these different things, you know, I would have good experience. And that's still a dream of mine, is to get rid of all the wires. But I pursued opportunities with Qualcomm. I pursued opportunities with NASA. I got this, particularly I pursued this fellowship. That's another way to get connected with NASA. A graduate fellowship. They called me, you're in the top 120. Called me and said, you didn't get the fellowship, but we're going to give you an internship. Gave me an internship. 2 days later, they said someone turned down the fellowship, so now I have a fellowship and an internship, 2 internships, because the fellowship came with another internship. Now 2 internships with NASA, and the guy that I worked for one of my internships, I kept in contact with him. I called him one day. He told me they was hiring. I applied, and that's how I got in with NASA. Next question.
Yeah, so next question is really interesting. David Wu from United Kingdom. Do you think instrument has a potential of usage in extraterrestrial terrestrial missions?
So I wish he was here to clarify what he means by extraterrestrial. But I don't know if he's saying other planets or other life forms. If he's saying other life forms, Boo, I have no idea. I'm sorry. I haven't even thought about it. You're above my head. I'm going to have to put some thought into that. If you're talking about other planets, at these frequencies, people typically don't measure planets. They typically measure, they can probably take measurements from other planets. It's most definitely can be used to take measurements of soil and you know, maybe foliage from other planets, even aerosols, but they typically use a much higher frequency. This is in the order, this instrument, if you looked at the presentation, it was on the order of 18 or 10 to 40 gigahertz, but it's in the terahertz range, in the higher hundreds of gigahertz range that they use to measure planets. Next question.
This is from M. Ibrahim from Egypt. Did IEEE help you to choose your career in NASA? How did it help choosing your career path?
Yeah, so, you know, what's interesting is that at the time, I wish I had time to tell this story, but at one point in my life, my undergrad is in math. And I was telling Preeti before this presentation that I took 1 year of electrical engineering courses because I knew I wanted to go into RF and microwave. Actually, I got into grad school by flirting with some girls from the Society of Women Engineers Conference, which I think is an IEEE organization as well. If it's not, the conferences was most definitely helpful because at that point you got a chance to kind of meet people, you got a chance to network. And at the conferences, the IEEE conferences, you kind of get a chance to see what is the latest and greatest and cutting edge technology. So I would say that's how they're really helpful. Next question.
Yeah, so if you're speaking about IEEE WIE, yes, it's IEEE, so okay, that's great.
Yeah, so that's how I got into grad school. I had nothing. I had 10 rejection letters, no, 12 double-digit rejection letters from schools, double-digit rejection letters from fellowships. I was flirting with this girl. We ended up being really cool, never dated. It would end up being my study partner at the University of South Florida. She connected me with some people that I was recruiting for the university. They flew me out to the university. I met my advisor. So, you know, I wouldn't be in grad school if it wasn't for IEEE conference. I probably wouldn't be at NASA if it wasn't for the IEEE conferences. And this one was the Women Engineers Conference.
Okay, that's awesome. Okay, so the next one, we are almost close to our end of the session. So the next question is from John, who's from India. What is the accuracy of the radar and the apparatus on the whole in the real environment versus that of the laboratory simulation? What?
Go ahead.
Yeah. So what affects the accuracy and how much is the variation?
Okay, so I can't speak to the radar. Once again, the radar was developed by Harris. The radiometer, we're still working on the accuracy. Right now, we're off pretty significantly. Even though I can show the variations in the snowpack, I'm still off by about 15% in accuracy. When really, I should be around up in the higher 99%. And I'm working on my calibration algorithm and my optimization to get the necessary accuracy. So for radiometer, our accuracy is up in the 90-something percentile. 99% is kind of close to what we shoot for. Next question.
Okay. So next question is from J. Kim, Japan. So this is about the presentation. Kim says the visibility of the slides is a bit low. So is it possible to get your slides? But I would like to answer on the second part, that the visibility. So once your internet streams, you could also watch it directly on our YouTube channel. So we will have this video archived on the YouTube, and it should be much better, right? Okay. So
right.
Next, yeah. Yes, Quenton. Okay.
I was saying, next question.
Yes. So the next question is from Mohsin Aziz from Pakistan. Can you throw some light on what type of signal processing techniques are being used in the system?
Yeah. So I used what they call filtering. I did a movement average filter on the data. So to get rid of the spikes, I pretty much did like in MATLAB, I did like a polynomial fit on the data. And I threw out data certain standard deviations away from above and below the mean. And that's how I got the spikes out. That's one signal processing technique. Another technique is just kind of housekeeping where, your data, your calibration load is related to a state. You use your programming to, find the indexes of those states. You put them all together, and we do moving averages, different things. I think that's kind of the most I could speak to in such a short period of time.
Okay. So those are the questions from today's session. Yes, Quenton?
No, I was just saying we got through all the questions, so that's great.
Yeah, that's correct. Should there be any questions, I will share Quenton's email ID in the next email I'll be sending to all our participants. So you could write directly to Quenton, and he'll be happy to answer your questions. So that comes to the end of our session. Special thanks to our partner, IEEE Young Professionals Microwave Theory and Techniques Society, and to the MTT-S Young Professional Coordinator, Tushar Sharma, for initiating this conversation with Quenton. Thanks to all our participants for joining us today. I will send you a feedback survey shortly. Please do share your valuable inputs and help us make the experience better for you. The next webinar is hosted in collaboration with ComSci 2016. It's a session on the IoT and the connected world we live in. It's a IEEE Young Professionals special panel. You could follow the updates on this on our social media, Twitter, and the Young Professionals Facebook page, also on our website. Please do write to us on young-professionals@ieee.org in case you would like to suggest any topics or speakers for future webinars. Thank you so much again. Thanks, Quenton, for the presentation today, and thank you all.
All right, you're welcome, and thanks for the opportunity. Thanks to Shar and Anjali, the people that I know who supported and logged on and asked questions. Everybody else who asked questions, thank you, Preeti, for the invitation, and IEEE Young Professionals.
Thank you so much.